In programming, it's often said that there's no need to reinvent the wheel. This phrase emphasizes the value of reusing existing solutions when they're available. If a solution to your problem has already been coded, then it's often best to use that pre-built solution that someone else has spent time and energy developing and testing, as opposed to recreating it yourself from scratch and likely running into many of the same challenges that they've already addressed. By reusing existing solutions, we can abstract away all of the difficulties of the problems that have already been solved, and instead focus our attention on building up more complex designs on top of them. If we don't waste time reinventing the wheel, so to speak, then we can focus our efforts on designing a cart. Now, when learning, particularly when learning foundational knowledge, we will be reinventing some wheels. We do this in order to learn how those wheels work. But in this video, let's look at some of the existing solutions already built into the Python language. Python provides many powerful built-in functions and libraries. These pre-built solutions work a bit like mini programs that someone else wrote. They solve some of the fundamental problems in programming so that we can focus our energy on addressing our own unique challenges. Let's start with built-in functions. These are commands in Python that are built directly into the language itself. They're ready for use immediately without any special preparation. These built-in functions handle common challenges, providing us with simple solutions. As programmers, all we need to do when faced with those challenges is then just call this built-in function that's already designed to solve it. We've already seen several of these built-in functions in Python. For example, the print function for displaying text to the screen, the input function for gathering user responses, and the type function for identifying the data type of a given value. These solve fundamental problems, which would otherwise become quite cumbersome in our own solutions if we had to solve them from scratch every time. But instead, Python gives us a very simple solution. Just run this command. Just say print and the value you want to print, and it magically appears on the terminal window. I don't know how it does it, but it works every time. These built-in functions, and lots of others like them, all work similarly. Typically, they go through an input, process, output syntax. So to use a built-in function is pretty straightforward. We call a function by using its name, and then we put a set of round brackets or parentheses after it. The purpose of having the parentheses after the function name are for containing the inputs or the arguments to that function. If there are no arguments, we just include a blank pair of brackets. And if there are multiple arguments, then we can separate them with commas. When that function is run, the function then processes through these inputs and provides some result or output. Typically, that result is important to our code, and so normally we'll assign it to a variable in order to be used in subsequent computations. So let's consider some quick examples here. So I'll open up the terminal. We'll go to the interactive Python shell, so just Python. So we'll start with a couple of variables here. So we'll say x equals 58, and we'll say y equals 100. Then let's say for our task, we want to know how far apart these two numbers are, but we don't care in which direction. That is to say, we want to know the absolute difference between x and y. So we can do some subtraction, so we can say x minus y, and then to get the absolute value, we can use a built-in function called abs. So here the function name is abs, short for absolute value. Then we put parentheses with our arguments inside. So the argument here will be the result of x minus y. It's not passing the subtraction operation into the function, it's doing the subtraction and then passing in the result. Then abs will do some processing of some kind, some magical black box operation, and it'll give us back a result, which is, in this case, the absolute value of our input. When we hit enter, Python tells us the value of this expression is positive 42, and if that value is useful to us, which normally if we're bothering to compute it, it will be, then we can store that value in a variable. And then we can use that value later on, anytime we would use this variable. So input, process, then output. Let's see some other examples. We've already seen casting functions like str. So I can say my string equals str of difference. So our input here is the value of the variable difference, which, as we've already seen, is the integer 42. The process is somehow converting that number into a string, and the output is the string value 42. In quotes. Another function that will be pretty useful later on is the len function for counting the number of characters in a string. So you could say len of my string. That gives us 2, because the string 42 has 2 characters. Or we could try it with a literal string value. So I could say len password, and that tells us 8. If we want to find the largest of several values, we can use the built-in max function. So I can say big num equals max of just 4 numbers, 5, 8, 2, 3, 9. Put a 1 just so you don't think it's the last one. And then I can say big num. And if we check, big num has the value of the largest input. We can also nest our function calls, which means we can use the output of one function directly as the input of another. So for example, I can say longest equals max len hello, len goodbye, or len anti-disestablishmentarianism. So notice that we're calling the function max with 3 arguments, each of which is a call to the function len. And if we check the result, it gives us the length of the longest of the 3 words. If it's not clear how this works, walk through it step by step. So first, each one of the len functions needs to be called independently, each on its own argument, and each returning a number as a result. So somewhere in the middle of this call, we had something more like longest equals max of, would be 5, 7, and 27. So you can think somewhere in the middle of this first line, it ended up at this second line here, and then the max call is just a standard max call on integers, which we've already seen from there. It's a good idea not to overly abuse the practice of nested function calls, though. As you might imagine, it can become confusing kind of quickly as the complexity of your statements increase. But it does often allow us to write simpler, multi-step instructions in a succinct way, and at times with improved clarity. Now, there are far too many built-in functions in Python to even list them all here, many of which we'll never even see in this course and you may never need throughout your entire career. Others, like the print function, you may use in every single piece of code you ever write. But generally speaking, the built-in functions all work the same way: input, process, output. Of course, as with all rules, there are some exceptions. The print function is a bit special that way. It doesn't actually return a value to our code. Instead, its purpose is to convey information to the person using the computer. That is, by displaying text on the screen. So we say print does not return a value to our code, but it has the side effect of putting text on the screen. So I can demonstrate that quickly just by saying something like variable equals print hello. So it prints hello to the screen, but if we ask what's the value of variable, it has no value, nothing comes out. So print doesn't return a value to our code, it just displays it to the user. Notice though, throughout all of the built-in functions, the concept of abstraction is front and center, because we don't need to know how the functions work in order just to say, apply this function to these inputs and give me back an output when you're done. The problems of getting user input or counting the number of characters in a string could in fact involve very complex operations, but the functions themselves are very simple to use. Beyond built-in functions, Python has an extensive collection of libraries. These are pre-written collections of functions and constants that aren't tied directly into the core Python language. That is, if we try to just use them without first preparing to use them, Python will say it doesn't know what we're talking about. However, these libraries do ship with the Python language. They're called standard libraries. So if you've installed the Python interpreter, all you need to do is import the specific library or libraries that you need into your program. The idea here is, if Python included all of its libraries into the core of the language itself, then the language might have many conflicts with names and become slow to resolve statements. So Python includes some core operations like print and input, which are used very often, and then has libraries which we can optionally add to each program when we specifically say that we need them. The syntax for accessing these libraries is still pretty simple. Before we can call a function from one of the libraries, we have to first use an import statement. So let's start with a simple example. So I'm going to make a new file called importdemo.py. And this is just a demo program to illustrate library usage in Python. So in addition to the built-in arithmetic operations and such, Python has a library called math, which includes more advanced mathematical operations. To access these operations, we start our code with the line import math. That's it, just import math, no tricks or tariffs, and now Python knows where to look when we ask it to use the math library's functions. For example, if we wanted to calculate the square root of a number, then we could say x equals 144, x root equals, and then we say math.sqrt, so math.square root, and then some input value. So the math library dot, and then the name of the function we want to use, and then we pass it in our argument. So using a function as before, except now we say, go into the math library to do it. That gives us back the square root of x, so we can then print that value out and test our code. So I can say print f square root of x is x root. So I say Python import demo.py. We run that and it says the square root of 144 is 12.0. Libraries can also contain constant values. So for example, we can calculate the square root of pi by saying pi root equals math.sqrt of math.pi. And print it out to see what we get. So print f the root of, and then I can say math.pi to, let's say, 3 decimal points is pi root. And we'll do that to 7 decimal places. Close our string, save, run our code. It says the root of 3.142 is 1.77. So again, we go into the math library by saying math dot, and in this case, we access both the square root function that way. We also say math dot, and we get the pi constant. So notice there's no parentheses after pi here. That's because it's just a variable name, not a function. So it just holds a value rather than holding a whole process. There's lots more functions available in the math library. If you want to see a reference, you can go to the Python documentation. There's a link in the slides here. So this is the Python documentation for the math library, and you can see there's lots of functions available and a few constants as well. You can click on any of them to get a description. So arcsine says returns the arcsine of x in radians. The result is between half negative pi and pi. There's your reference for that. And that actually covers the basics of importing libraries. So math is a separate module. It's been written by somebody else and is stored somewhere else on your machine. Importing it gives us access to all the functions and constants defined within that math module without having to write any of those functions ourselves. There are many different libraries available, some made by Python, some made by others, but they all work the same way. We say import, then the name of the library, and then when we want to use a function from that library, we just say the library name, dot, and then the function name. Okay, next let's see another important library, the random library, which provides functions for generating random numbers. We'll start with a quick demo here. So in order to use the random library, step 1 is to import it. So up at the top here, we'll say import random. Now technically import statements can be put anywhere in your code, but by convention it's considered good practice to put them all near the top of your file. This way they're all in one place, and so when you open a script you can immediately see the libraries that it depends on, which becomes more important when some of them are from outside of Python's standard libraries. Once we've imported random, we can then use its functions. And again, there are many functions in the random library, and we'll just use a few of them here. So the random library lets us generate random numbers, starting with generating a random integer. So we can ask the random library to get us a random integer by using the randint function, which returns a random number between 2 input values. So for example, if we wanted to simulate rolling a dice, we could say dice roll equals random.randint, and then pass in 2 values, so we say 1 and 6 for a 6-sided die. And if we want to see what we got, we can print that value out, so we can say dice roll, and then dice roll. Save and run our code. And notice it rolled a value between 1 and 6 here. If we run it again, we get a different number. If we run it again, a yet different number, but all within the range 1 to 6. So random.randint generates a random integer between 1 and 6, and it's inclusive of both its ends. If we try running it a bunch of times, we should eventually get a 1 and a 6, oh there we go, as well as all the numbers in between. There's another useful function called randrange, so I can say print I'm thinking of a number, and then we'll say random dot, and then randrange. So instead of randint, we say randrange, and we'll just say from 1 up to 10. And this works similar to randint. It will generate a random number, except instead of being inclusive of both ends, it's exclusive of its end value. So this would generate a random number somewhere between 1 and 9. Save and run our code, see this a few times. We got a 9 there, 2 there. We can run that a few times. We'll get random numbers between 1 and 9 inclusive, but we'll never actually reach the value 10. So randint, we could say, is inclusive, so this would be the range from 1 to 6, inclusive of both ends. And over here we'd say randrange would give us a value between 1 and 10, exclusive of its last value. The reason why randrange might be useful, or why Python offers both, will be clearer later on in the course when we start working with lists of values. For now, just know that rand_int is inclusive and rand_range is exclusive, but they both give us random integers. If we want to generate floating point numbers, we can use the random function from the random library. So I can come down here and say, generate a random float. We can say r equals random.random. No arguments, and it just returns us a floating point number in the range from 0 to 1. So print a random float, and then we'll just print out r. You can use these numbers in other ways than just printing them, but for the sake of demonstrating the random library, we're just printing them as we get them. So there's a random float between 0 and 1. We got 0.59. Run it again, and we get a different random float, which is pretty close, but let's try another one. Keep running, and we get all sorts of different random numbers. But notice it never goes up to 1. So this is a random number in the range between 0 inclusive and 1 exclusive. So it might be 0, but will never be 1. So it's between 0 and 0.99999 continued. So with these calls to random in place and without changing our code, every time we run our code we get different outcomes because we've included some randomness into our program. Now if we wanted to have a larger floating point number, say if instead of between 0 and 1, we wanted between 1 and 100, then we can do some math on the result of generating our random number. So I can say r equals, and then do a little bit of math. So we have our original random number there. We can multiply that by some large number to make it a larger range, and then we can shift that with some addition. So this would say between 1.0 and 100.0, inclusive of its first value and exclusive of its last still. So here the multiplication expands our range across 99 possible values, and the addition shifts that range to start from 1 and end at 100. And if we want, we can print that out as well. So print a large random float is r. And there you go. Now we have a random number between 1 and 100. If you run it a lot, you might eventually see it throw a 1, but you will never see it throw 100.0, but it might be up to 99.99 repeated. Now, the values generated by a random library are actually called pseudo-random numbers. Kind of like how pseudocode is almost code, but not quite. Pseudo-random numbers seem random to us humans, usually, but are in fact not random at all. And this is because, as we've learned, computers can only ever follow instructions. So how would it be possible for them to do anything unexpected or random? So in order to emulate true randomness, a computer would have to access something in the real world that imbues it with that randomness. Either some action of a human, or the bubbling of lava lamps as in Cloudflare's cryptography lab, or some background radiation from space, things that can't actually be predicted. But that's a lot of work. As a simpler alternative, most programming languages support the idea of pseudo-random numbers. And these are actually computed by just following a deterministic formula that seems random enough to prevent most humans from being able to predict what the next number would be. Now these formulas can be provided a fixed starting point called a seed, and from there it will generate a sequence of random seeming numbers. However, if we start with the same seed each time, then we'll get the same sequence of random seeming numbers every time we run it. So if up here in our code, before we start generating any random numbers, I could say random.seed, and then I can put any value here, 1, 2, 3, 4. And this creates a fixed starting point for our random numbers. So we can use any number we want. 1, 2, 3, 4 is just a random number out of my head. But so long as it's the same seed every time, then we'll get the same random sequence every time we run our code. So let's save and run this code. And we get the values 4, 2, and then 0.007. And if I run it again, we get 4, 2, and 0.007. If I run it again, there you go. And we can change this random seed. Just add 1 to it, and we'll get completely different random numbers, 6, 7, and 0.53. So there's not an obvious correlation between the number that you're seeding and the values that it generates, but if you're using the same seed every time, then you're going to get the same sequence of random numbers. If we change that seed, then we'll get a different sequence of random numbers, but again, we'll always get the same random sequence with the same seed. So seeding random numbers can be useful, for example, if you're using Python to perform some scientific simulations. You often want to have randomness in your simulations, but a repeatable random sequence means you can go back and reproduce any of your observed outcomes. If we don't provide a seed, then the pseudo-random numbers still work the same way, but Python will then use a default value to start. This is usually something like the systems clock, so that every time you run your code, it comes up with a different value. So The random library lets us generate pseudo-random numbers, which can make our code more interesting by creating unpredictability in a space where normally computers only follow instructions. As with the math library, there are many more functions available in the random library, and you can view the Python documentation by following the link in the slide. The core functions that we need, though, are listed here in the slide, randint and randrange, which do pretty much the same thing, but with the key difference that randint includes its last value, and randrange does not, and random.random for generating floating point numbers. Okay, returning back to our demo example here, I just want to demonstrate some of the other things you can do with import statements themselves. So let's scroll to the top. So we have two import statements here, import math and import random. But there's an extended syntax for all the different ways that you can import things into your code. I won't go into all the different options here because the basic import statement that we've just learned is probably sufficient for all of the applications in this course. But if you don't like the default way of importing a library and then always having to type that library name and then a dot and then the name of the function that you want to use in order to use it, so having to say random.randrange, for example, then there's a few things we can do to shorthand these expressions. The first thing we can do is change the name of the module within our code. So if, for example, I don't like having to type random every time, or I already have something that's named random in my code, then I can import random as something else. So I can say import random as, I'll say RDM. Now notice our editor has told us there's something wrong with the word random everywhere now, because the random library everywhere in our code now needs to be called RDM. So we can do that really quickly. Just replace random with RDM, and swap, swap, swap. No, not that one. Not that one either. Okay. I accidentally did this one. There we go. So now everywhere where we had before random.the function, now we have RDM.the function name. Now the specific name you choose here, so I've chose RDM, but the specific name you choose here is just a variable name. It can be whatever you want it to be, but you should note that when changing the names of standard libraries, you might end up making your code a bit harder for other programmers to read if they're already used to seeing the default names. Otherwise, it makes no difference to the code itself. So we can save and run our code, and we get all the same sort of random numbers. So this is useful if you want to shorten the name of a library or reduce the amount of typing that's required to use it. Another thing you can do with imports is if you don't want to import the entire module, you just want to import a specific function. So for example, if you only needed to import the square root function, then what we could do instead of importing all of math is say, comment that out and say from math, import sqrt. Or in this case, since I'm also using pi from the math library, I could say square root comma pi. And now this will go into the math library and import the square root and pi functions, well, the square root function and the pi constant, directly into our local namespace. So I no longer need to tell Python to go to math dot in order to find square root. I can just say square root and pi. Like that. Save our code, try it out, and everything works the same way. The square root of 3.142 is what it is. So it generates an estimate of pi and takes the square root of that estimate. So we're still accessing the math function, it's just we've done so in a slightly different way. Another way of doing the same thing that's pretty commonly used, if you don't want to type out all the different commands that you want to import, is instead of naming them all, you could just say, let's comment this out, you just say from math import star. And that does a similar thing. It says from math, import everything. So the star here is called a wildcard, which tells Python to grab everything that's in the math library and put it into my local namespace. So we can save our code and run it, and it still works the same way. So now, without having to tell it specifically to import square root and pi, we can now access square root and pi directly from the math library. Which of these options you choose is entirely up to you. You could argue that typing out all the names is a bit safer because you don't know what's all being imported when you just say import star, but technically an import doesn't move any code around. It just tells Python where to look. So when we use an unfamiliar name like square root or pi that's not defined in our own file, the import says before giving up and throwing an error to the user, check in these libraries for an answer. There are also many more libraries available, several more in the Python standard libraries, and many, many more out in the big wide world. In fact, there's actually a running joke that Python solutions are all just one line long because you can just type import solution at the top of the file and you're done. And while this is a bit of a joke, it also has a bunch of truth to it. The available library support in Python is very extensive, so when you're out in the world solving real problems, you will very likely need to first explore what available solutions already exist that are ready to be imported into your work. Oftentimes, if you can solve your problem this way, that would be ideal. By reusing existing solutions, even just for parts of our problems, we can save time, effort, and maybe even money. However, throughout this course, as I mentioned, we will be rebuilding solutions from scratch for many problems that may already have been solved, for the purposes of expanding our own understanding. So if you're faced with a difficult problem and you find yourself looking online for solutions, make sure you're seeking to improve your understanding and not just seeking to eliminate a problem. That is, Googling or discussing with an AI to help yourself understand a problem is good, but copying solutions and calling them your own without understanding them is bad. In university, copying solutions without understanding them could lead to an academic misconduct violation, which can affect your grades or maybe even delay graduation. In the real world, copying solutions you don't understand could lead to legal problems that cost both you and your company real money, or maybe even something worse. So, when you're tasked with solving a problem, it's important to find out what's available online, but it's also important to understand those solutions before you use them. It's very easy to copy and paste code that you don't understand and end up having more issues than you started with. Alright, that's it for this video, and now we've covered the fundamentals of Python programming that underlie all of the code that we'll write moving forwards. In the next few chapters, we'll go over some of the more expressive forms of statements that we can use to make our programs more fully fledged with decisions and repetition. But we're building up on the core material that we've covered over these past several videos. So make sure you've understood it all, don't forget to blink, and I will talk at you in the next video.